Dear students, I am Professor Archana Pandey from Department of Chemistry, Dr. Hari Singh Gaur Vishwavidyalaya, Madhya Pradesh. Today I am going to deliver my lecture on microwave spectroscopy for diatomic molecules. Let me introduce why we are studying the microwave spectroscopy. The first one is we can calculate the bond distance of a diatomic molecule which are in gaseous state. You know very well that in gaseous state it is quite difficult to measure the bond distance because gases are free to move in space. But with the help of microwave spectroscopy, we can calculate easily the microwave spectroscopy. Second point is that we can calculate the dipole moment of a diatomic molecule. Similarly, we can calculate the molecular geometry if the molecule is polyatomic in nature, the structure at equilibrium if the molecule is polyatomic in nature. Similarly, we can calculate the electronic dipole moment just like quadrupole moment, dipole moment, etc. Now, the interesting point, we can calculate the interstellar gaseous bond distance and also precise observation of translating stereochemistries and their conformation as well as verification. Now, you are curious to know about the introduction of microwave spectroscopy. In a very simple way, my students, I will explain you. Microwave spectroscopy is nothing else. It is a spectroscopy which is produced by the absorption of microwave radiation is known as microwave spectroscopy. So, it is a very simple one, keep in your mind. The rotational energies correspond to the microwave region, as I have already stated here, of the electromagnetic radiation, and range is the 3:10 raised to the power 10 to 3:10 raised to the power 12 hertz energy range, and about 10 to 100 joule per mole. After absorbing the microwave radiation, molecule start rotation. But remember one thing here, that energy is here quantized, means it received as in the form of photon or the quanta, as the Planck has stated. Microwave spectroscopy is also referred as rigid rotator. We assume that molecule is rigid and does not vibrate. But we know that this assumption is quite theoretical. Just like a dumbbell, you rotate the dumbbell in any direction or any position, but the distance of the dumbbell is always constant. Similarly, the bond distance of a rigid rotator is always constant. Now, what is the basic principle of the microwave spectroscopy? I will give you the fundamental points which you keep in your mind for examination or for other purposes. So, now let come to the basic principle. When a molecule having a permanent dipole moment, it is very necessary in case of microwave spectroscopy. The molecule is rotate. How it rotate? When we bombarded the microwave radiation onto the molecule, if the energy is matches, means the resonance, then molecule absorbs the microwave radiation and goes to higher energy state and start rotation. Here, one point I want to clear you, that when the molecule goes to higher energy state, you know very well that the higher energy state is most unstable state, and therefore molecule try to come in ground state, and thus the microwave spectroscopy produces absorption as well as emission spectra. That is the rare character of the microwave spectroscopy, that Both type of the spectra are included in this spectroscopy. Now, the fundamental points which you can note it down, that is the molecule start rotation with high energy. Now, remember here that this energy is quantized. I think you are the student of BSc 5th sem, you know the meaning of quantized, means the energy is absorbed in photons, in quantum, or you can say the pockets of the energy. Here is the controversy that if the molecule is rotate, then there is a vibration is also possible. But dear students, you know that vibrational energy is 1000 times greater than the rotational energy. Therefore, after the absorption of microwave radiation, molecule vibrate very little bit, and therefore it can be neglected. And you can say after absorption of microwave radiation, molecule only rotate. Second point which you keep in your mind, that is the bond length is almost constant, and therefore it is referred as the rigid rotator. I will explain later what is the rigid rotator. We assume that diatomic molecule is having point mass. What is the meaning of the point mass? I will explain later. We assume that molecule is having point masses M1 and M2. Now I will explain you how to obtain the microwave spectra. It is very simple. Consider that the point masses of a diatomic molecule are having their own electronic structure. Two fundamental conditions are required for microwave spectra. First one is the dipole moment and second one is the bond length. You are familiar with the both term, but I will explain in little bit detail. Bond length is second parameter. We assume that molecule is rigid. It does not vibrate. The rigidity referred here that average bond distance does not change, and the harmonic amplitude of vibration is very small. It is concerned with transition between rotational energy levels in the molecules. The molecule gives a rotational spectrum only if it has a permanent dipole moment. That is the basic needs of the microwave spectroscopy. Now let me clear what is the rigid rotator. Rigid rotator, we assume that molecules are having 2 point masses M1 and M2, and the center of mass is fixed, just like a pole you fixed on earth. It is tightly fixed on earth, and two strips are attached with the pole of a definite length. Similarly, the atom A and B, whose point masses are M1 and M2, are attached with the pole. Now you rotate the strips many times, but the distance is always constant. Same thing is here also. The center of mass is constant, and the point masses M1 are located at the R1 distance from the center of mass, and the point mass M2 is located at R2 distance from the center of mass. It is clear for you? Now, the bond length is the total of R1 plus R2, that is capital R. Now, this molecule is not move away from each other, and the bond length is almost constant, as I have given you with the example of a fixed pole. The center of mass is fixed, and you can say very frankly that molecule does not vibrate. Now, therefore, it is called rigid rotator. In microwave spectroscopy, after absorption of microwave radiation, molecule can be broken into 5 segments. First one is shape, second one is the 3 rotational axis and moment of inertia. 3 rotational axis, one is the bond axis, first one is the bond axis, second one is the perpendicular to the bond axis and third one is the perpendicular to the screen. And we assume that molecule is rotating in all 3 axes. I have already discussed with you that moment of inertia is an important parameter for the microwave spectroscopy. Shape, every molecule is having, every atom is having their own electronic structure, and this electronic structure is very important in case of rigid rotator, or you can say in case of microwave spectroscopy. How you will get the microwave spectra? For getting the microwave spectra, you need only 2 important things. First one is the molecule is having dipole moment, and second one is molecule behave like a rigid rotator, as I have already discussed with you. You know very well that dipole moment arises due to the charge separation in a molecule, just like in HCl. Hydrogen is having positive charge and chlorine is having negative charge. I explain you what is the dipole moment. As you know, you learned this dipole moment from your 12th classes also. That dipole moment is a vector quantity and it is given by a simple formula, D is equal to Q into R, where Q is the charge of the atom and R is the bond distance. One question keep in your mind, that if the molecule is having dipole moment, it absorbs microwave radiation. So how the transition takes place? The transition is very simple, that you see here A plus means H plus ले लीजिए, you can take the H plus ion. So H plus ion is going towards direction and B plus is upward direction. Similarly, again A plus is going to upward direction and B plus is going to the downward direction. It is so simple. Now, one thing, it is for discussion only with you, that HCl and carbon monoxide both are having microwave spectroscopy. Why they are having microwave spectroscopy? Because they have dipole moment. If you can say that hydrochloric acid and carbon monoxide are microwave active. Why they are microwave active? Keep in your mind, because they have dipole moment. Similarly, hydrogen and chlorine does not show microwave spectroscopy. What will be the answer? You can actually answer that they do not have the dipole moment. Rotational spectroscopy is only applicable in gaseous state. You remember that. It is applicable for only in gaseous state, and you can measure the bond length of the interstellar system. Means you can measure the bond length of the gases, those are in stars or those are in interstellar system. It is not applicable for the solid and liquid, because the energy of the microwave radiation is not quantized, because in liquid and solids it quenched due to the collisions. My questions here for you, a very simple question: which of the following molecules show rotational spectrum and why? So first one is the bromine. Question with you, that is bromine is showing microwave spectroscopy? Answer is no. Why answer is no? Because it does not have charge separation. It does not have dipole moment, and therefore it cannot give the microwave spectroscopy. Second question is that, is HBr, hydrobromic acid, will show the microwave spectroscopy or not? Answer is yes. Why answer is yes? Because here is the charge separation, H plus and Br minus, and it possesses the dipole moment, and therefore it is a microwave active. Third one is the CH2. CH2 does not show the microwave spectroscopy. Why? Because it is having zero dipole moment. If the dipole moment is zero, then there is no question of microwave spectroscopy. I think you can understand the things. Assuming that the center of mass is constant, it means it does not rotate. As I have already stated that there are three axes. First one is the bond axis, second one is the perpendicular to the bond axis, and third one is the perpendicular to the screen. And we assume that, again I recall for your memory, that we assume that molecules after absorbing microwave radiation, they rotate in all three axes: bond axis, perpendicular to bond axis, and perpendicular to screen. They possess the moment of inertia. You know the moment of inertia is equal to m1 r1 square plus m2 r2 square, where m1 is, you recall your memory that m1, m2 are the point masses of atom 1 and 2, and r1 and r2 are the distance from the center of mass, and the bond length is the capital R. The moment of inertia of the bond axis is 0. Why it is 0? Because bond axis is fixed. R1 and R2 are the 0 for the bond axis, and therefore moment of inertia is 0 for bond axis. But for two axis it is same. Means if you consider one axis as A, bond axis as A, and perpendicular axis as B, and another perpendicular axis as C, then you can write that IA is equal to 0, moment of inertia of the bond axis is 0, but the moment of inertia of B and the moment of inertia of C are equal, and they are equal to the m1 r1 square plus m2 r2 square. Now, the rotational kinetic energy, it is a very important one. Why I am taking only kinetic energy? One question arises in your mind, because we assume that molecule is not vibrating, there is no thermal motion, and therefore no question of the potential energy or other energy. Therefore, we consider here rotational kinetic energy. Means when molecule rotate, it possesses only kinetic energy, and it can be given by a simple relation, that is rotational kinetic energy Ej is equal to the Eja square. A suffix A is used for the bond axis. Since its moment of inertia is 0, therefore I have neglected that axis. So, rotational kinetic energy is equal to the Jb square upon 2I plus Jc square upon 2I. Since Ib and Ic both are the same, therefore you can write the simple equation J square upon 2I. From quantum mechanics, you know very well that moment of inertia is related with the Hamiltonian by a simple relation, that is the Hamiltonian is equal to the cap J square upon 2I. Now, you derived the I is equal to, from in equation first, I is equal to m1 r1 square plus m2 r2 square. It may be written as mu r square. Now, again one question come in your mind, that what is the mu? Mu is the reduced mass or active mass, and it is equal to the m1 into m2 upon m1 plus m2. Here again I recall your memory that M1, M2 are the point masses of diatomic molecule. Now here you see that this equation Hamiltonian is equal to cap J square upon 2I can be calculated with the help of quantum mechanics, with the help of Schrodinger wave equation. Although the derivation of this Schrodinger wave equation is not given in your syllabi, therefore I have taken the short form of this Schrodinger wave equation, that is H psi is equal to E psi. Hamiltonian H cap psi is equal to E psi. Hamiltonian psi is equal to E psi. Psi is the rotational eigenfunction. It is very important function. I think you might be listen about the eigenfunction. Now this psi here in equation 6 is equal to the H minus H cross square upon 2 pi del square psi is equal to E psi. It may be written as del square psi is equal to minus 2IE upon H cross square psi. But E is having its own value, that is E is equal to Bj, J plus 1. Now J is the rotational quantum number. It may be 0, 1, 2, 3 and so on. And here B is a constant. And it is not a simple constant. It is actually the energy unit constant. It possesses a number of meanings. I will explain later. The unit, if you want to calculate the unit of rotational energy, so we can use the whole formula by putting the value of B in equation E Bj J plus 1. So final formula comes like that: Ej rotational energy is equal to the H square upon 8 pi square I J plus 1. Now if you want to find out the unit of this formula, so it may be written as kilogram meter square second inverse whole square upon kilogram meter, and it can be calculated as kilogram meter square second inverse joules. We know that in a spectroscopy the spectrum cannot be represented in terms of joules. It may be presented in meters, centimeters, nanometers and so on, and therefore we use another method to find out the spectrum in unit of meter, centimeter or nanometer. Quantum says that the radiations are absorbed in bunch of quanta, and that is the photons, you know very well. So and Planck's given a simple formula, E is equal to h nu, where h nu is the photon, means any molecule absorbs the energy, it absorbs the quanta, that is h nu, and this is the quantization of the energy. This is the quantization of the any spectroscopy. So if you want to represent your spectrum in frequency, in terms of frequency, so then the formula is rotational energy is equal to h nu. If you want to represent your spectra in terms of frequency, the automatically unit becomes hertz or second inverse. And if you want to represent your spectra in terms of wavelength, automatically unit change, it becomes meter or the centimeter or the nanometer, and the formula becomes, you know that nu is equal to c upon lambda, where c is the velocity of light, lambda is the wavelength and h is the Planck constant. If you want to represent your spectra in terms of wave number, unit is automatically changed, and unit, what will be the unit? Centimeter inverse or the meter inverse or the nanometer inverse, and it is written as Ej energy of rotation is equal to hc bar nu. Now I give you a clue that if you want to represent the rotational energy, simple rotational energy, which is expressed in terms of joules, you use the capital EJ, right? And if you want to change the unit of your spectrum, that is centimeter inverse or the meter inverse, then you use epsilon j. That is a very tricky point which will help you. If you see capital EJ, it means spectrum is represented in terms of joules. If you see the terms that epsilon g means unit is centimeter inverse or the meter inverse, and the EJ epsilon j, although it is energy terms, but here epsilon j is equal to EJ upon HC, and the formula is h square upon 8 pi square IC j plus 1. The meaning is the same. Now, EJ gives the allowed energy level of the rigid rotator in centimeter inverse. That is our aim. One question comes in your mind, that what is the spectrum? Spectrum is nothing that a systematic arrangement of the lines which is obtained by absorption of radiation is known as a spectrum. So, when molecule absorb microwave radiation, it absorbed and goes to the higher energy state, try to come back to its ground state, thus you obtain the absorption spectra and the emission spectra, all right. And the systematic arrangement of this absorption and emission spectra is microwave spectroscopy. Why it is called microwave spectroscopy? Because it is obtained after the absorption of microwave radiation, nothing else. Now, in order to discuss the spectra, we have to consider the difference in energy level, because microwave after absorption of microwave, molecule is a start rotation. So, if molecule is raised from level J 0 to J1 state, then the energy difference del E is equal to Bj j plus 1. It can be solved like that, B1 plus in bracket 1 plus 1 minus B 0 0 plus 1. Why you taken 0? Because your rotational energy level is 0 and the result becomes 2B. Now, you see this clear picture of the spectrum here, and with the help of this spectrum I will explain the things. Similarly, if the molecule is raised from J1 to J2, the result is 6B minus 2B, that is 4B. In general, these are the two examples. In general, you see in the graph, when it goes from 2 to 3, the energy difference is 6B. Similarly, when it goes from 4 to 5, the energy difference is 8B. Similarly, when it goes to 4 to 5, the energy difference is 10B. So, here you find that there are simultaneous 2B. What is the rotational energy change? It is 2B, 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 2B. Means equally spaced lines are obtained in microwave spectroscopy. That is a very interesting character of the microwave spectroscopy. Equally spaced lines with the spacing of 2B, and it is given in the spectrum. A general formula you can derive for the equal spacing, that del E means energy change is equal to B j plus 1 into j plus 2 minus Bj j plus 1. You can solve this one, and finally you find that change in energy of the rotational transition is 2B j plus 1 centimeter inverse. Thus, we find a spectrum having a series of lines 2b, 4b, 6b, 8b, so on, and this is shown in this graph. What about the energy? If the rotational energy level is 0, so then rotational energy is 0. If the rotational state is 1, so then the energy is 2b. Similarly, if the rotational state is 2, then energy is 6b. Similarly, if it is 3, the energy is 12b. So, its graph it can be calculated with the help of formula, and I will explain number of examples with you how to calculate the energy change, how to calculate the rotational levels. In explaining a spectrum pattern, we have considered that transition occurs between adjacent energy levels, means step by step. Of course, this is one of the conditions for getting microwave spectra. In other words, it can be said that transition is allowed only one of the state is odd and other is even. Odd to odd or even to even is not allowed. Means if one state is, suppose one state is odd and another state is even, then transition is allowed. If both are having even state, then transition is not allowed. That is a rare character of the microwave spectroscopy. I will discuss with you in next lecture with few examples of the calculation of the bond length, moment of inertia, rotational energy and number of spectra in next lecture. Thank you very much.